Okay, so thanks very much for the introduction. I'll try and keep this relatively short. So I was asked to speak about the CKN bound and entropy bounds, and I have to say a disclaimer at the beginning here. What I have to say is mostly based on this paper with Tom Banks and this paper with Nikita Blinov, and a little bit on these other two. It's, I don't think, going to be terribly obvious whether this has some direct connection, at least to ordinary types of swampland ideas and the swampland program at large, but that's also part of the question, the just general question I'll pose at the end, which is, does this have anything to do with the swampland bounds? And I've put this joke here because it's going to be one slide of the simplest thought experiment in the world, and then rather aggressive extrapolation of that idea. Okay. Okay, so the Cohen Kaplannelson bound is really a completely trivial thought experiment that leads to a very confusing and poorly understood result. So the thought experiment that they pose is take a hot box, and if the temperature can be as high as the UV cutoff lambda, so here I'll just work in three spatial dimensions for the moment, then you don't want this thing to collapse to a black hole, so you say, all right, let me bound the Schwarzschild radius by L, and that gives you immediately this connection between the box size, 1 over root box size, and the UV cutoff lambda. And what's very strange about this is that it involves both the UV and the IR cutoff, and it's not at all clear at first sight what this means. So this is, in the modern parlance, this is some example of UV-IR mixing, although the word mixing is not really that relevant here. You know, it's 2 lines to get to this, and then the hard work is answering what this means. There have been a bunch of papers recently, particularly in the more phenomenologically oriented community, trying to apply this and see whether it means something measurable. And that's largely driven by the original interpretation given by CKN and a modern update by Cohen and Kaplan, and then most of the other recent papers, in which they just interpret this formula at face value and say, okay, these are UV and IR cutoffs that I'm going to stick onto my Feynman integrals. And this leads to extremely strong effects, even on completely ordinary processes that you might have said had nothing to do with quantum gravity. So for example, if I put ordinary IR cutoff on the G-2 one loop diagram, then it enters as a 1 over L. The UV cutoff is a 1 over lambda squared. And I'll just quote from their paper, our best strategy to reduce sensitivity to strong gravitational effects is to minimize the combined UV and IR corrections. And the reason that this thing has a stationary point is because we're going to impose this, this correlated relationship between the UV and IR cutoffs.
Patrick, can I ask a question?
Yeah.
So what is L supposed to be? Am I doing things in a box? It's like if I'm doing this for QED, is this like a metal plate?
Yeah.
Or...
Yeah, we will not be very careful about what the boundary conditions are here. So a small spatial 3 torus is fine too, or a large spatial 3 torus, or a box with Dirichlet conditions or whatever. But yes, okay. it's some IR cutoff that's. I'll be slightly more precise about that in a moment, actually.
Could it be the de Sitter horizon?
I will also say some more about de Sitter in a minute. Yeah, that's a good question. It turns out not quite, because there's a maximum black hole size in de Sitter, but you can adjust this a little bit and get a different bound that applies in de Sitter. So for the moment, just think about flat space with some IR scale.
Okay, thanks.
Yeah. Okay, so you plug in that relation to this formula, and I've just taken a screenshot from the recent Cohen and Kaplan paper on this, and you get these funny kinds of scalings for the UV and IR cutoff if you take this extremization seriously. And they say, okay, we're not pretending to compute corrections to electron G-2 from quantum gravity, but only an intrinsic uncertainty to the calculation in an effective theory that excludes gravity. And these kinds of scales that you get here are kind of weird. It's like a UV cutoff of 200 GeV and an IR cutoff of 6 centimeters. So, all right, so the final result is a correction to G-2, of which much has been made recently, that goes like a root of 1 over m Planck, which is, again, a rather weird scaling. And these corrections are not that far off within an order of magnitude or so of both the experimental and the theoretical uncertainties on G minus. Well, that's true for the electron, not for the muon. The muon is not competitive.
Sorry, Patrick, I just got lost. So these are the UV and the IR cutoff that you get if you want to cancel these corrections. So it's an output. It's not the.
Yeah, or perhaps not. It's sort of maximum cancellation. So it's the minimum of this correction given the correlation between lambda and L implied by the CK and bound. So you don't demand that these cancel, but you demand that you're at the minimum of the combined correction.
Okay, so you cancels as much as possible.
Exactly.
All consistent with the bound. I see.
Yeah, exactly. Okay, so this certainly looks quite ad hoc. Why should we do this? And it's clear that this is not even going to be sort of theory independent. QED Wi-Fi is something that's on the scale of centimeters or something. So a 6 centimeter IR cutoff, we're quite sure there is no such cutoff on the QED Hilbert space. So it has to be very process dependent, however you're going to impose these cutoffs. And then you get enormous corrections. It doesn't look like anything that you would get in perturbative string theory, certainly. So I would like to propose an alternative interpretation, which is much gentler than this. So if we go back to the original thought experiment, it's associating a length scale actually with every temperature, not just the UV cutoff. We plugged in a UV cutoff, but it's associating a length with every temperature. And then we can say, okay, the temperature is the typical particle energy in the hot box. So let's take the length scale now, which is associated with every one particle energy level, and say that that's providing the spacing of the states in the density of states. So in one dimension, if we have particles in a large box, then the energies are equally spaced very finely like this. And if we think about a small box, then they become more coarse. And so the idea here is that the box size will take the L dependence of the density of states and replace it by this energy dependent thing so that we get a scale dependent depletion. And in 3 spatial dimensions, these are no longer evenly spaced even for fixed boxes, but this is the type of thing that we'll use. So for low energies below the CKN cutoff for a given box size, if we take some fixed box size to be any other relevant IR cutoff, we'd look at low energies, and we'll just use the ordinary density of states, L cubed E squared for free relativistic degrees of freedom. And above that cutoff, now we'll replace the L dependence, the L cubed here, by L of E cubed. So that gives us this rapidly falling depleted density of states. And just as an aside, this is not that crazy, because we sort of expect something like this in holography. In ADS-CFT, for example, if we look at the bulk QFT entropy, it grows very rapidly with the temperature. It is finite. But the dual CFT has a much slower growth of the number of degrees of freedom with temperature. And so we see that there has to be some kind of power law depletion of the quantum gravity degrees of freedom relative to bulk QFT. And other kind of qualitative models of holography show the same thing.
Patrick, can I ask?
Yeah.
So when you do it in flat space, the physics of what you're imposing is you're just not counting in loops any state which would be within its Schwarzschild radius, right? That's kind of what we're demanding that the effective box size is getting smaller as I go to higher energies. Right, but isn't that a proxy for you to saying I want to throw out every state in which this one my reaction is strong and therefore shouldn't run in Feynman diagrams? Well, these are one particle states. None of them are black holes. So it's really we're changing the one particle states to match behavior that we need in order to not count things that need to be unphysical at finite temperature. But the finite temperature things are highly occupied. I was going to ask that the change, the mechanisms are, I mean, in ADS, the mechanism for that change in temperature is just the curvature of ADS, right? So there we understand, right? Like the wave functions of single particle states, they behave differently when the wavelengths are very large. This is, yeah, but this is correct even in ADS for the entropy of bulk QFT. Bulk QFT cannot be correct. I understand. Yeah. Okay.
Patrick, can I ask you a question about the treatment of the infrared cutoff?
Yes.
I mean, in gravitational system, is that clear that you could put a sharp cutoff on the length?
No. So you're
Where
asking,
it's
can I
both.
really talk about hard boxes in gravity?
Mm-hmm.
Well, there's nothing formally wrong with applying Dirichlet conditions to consider manifolds with fixed boundary 3 metric in gravity. We can do that.
But for instance, would you expect how you treat the infrared cutoff would affect the expansion that CK and have written down? I mean, this is a sharp cutoff that they imposed.
They impose a hard, yeah. I don't know. I don't know how precisely we can interpret anything from this thought experiment. I'm going to talk about a specific way to impose this conjectured depletion in a minute, but I certainly wouldn't be wedded to it. As Miguel alluded to earlier, we could ask about things with finite volume spatial slices like de Sitter. And in that case, we have to reformulate the bound a little bit, because hot boxes can't be arbitrarily large, black hole radii can't be arbitrarily large in that system. They can't even be of horizon size. So that will turn out not to make a huge difference in the kinds of results that that I'll report. But yeah, I would say that this is something that it's interesting because you can apply it on scales that are much smaller than the horizon size if you want, and it's just a scaling argument then. Am I getting a black hole or not? Okay, this is the kind of bound that I should require. What does it mean? I don't think that it makes a lot of sense to just put cutoffs on Feynman diagrams, but maybe this this depletion is a little bit more motivated.
Thank you.
Okay. All right. So one thing that that results from either treatment, hard cutoffs or from this depletion, is that the total number of degrees of freedom is very UV finite. You integrate that density of states, for example, and you get an a to the 3/4. And so the general slogan, which was articulated by Tom, is that in quantum gravity, the number of states that can be well modeled by local quantum field theory might be much, much less than the total number of states in a holographic theory. So we get this sort of entropy bound and effective field theories of a to the 3/4 versus a holographic bound of order A. And I put a footnote here. There's a very well-known factor of n to the 1/4, where n is the number of light fields in this formula, which can certainly compensate if n scales with the system size, if n is enormous. And that actually has been used somewhat effectively in various swampland conjectures, but for what I'll say today, that's I'll hold that n fixed and small and can neglect it. Certainly, if anything,
Can I
like
ask some question?
Yes.
So I would like to understand the interpretation of the meaning of the cutoff a little bit better. So if I follow the original argument, the cutoff is a cutoff for average energy density, right? Because you compare the total energy in the box with then they calculate the size of the black hole and then compare with the size of the box. So that means that, for example, for example, Miguel asked, can the size be the jitter radius? And so that would be an extremely unusual situation, because that would happen when the average energy density in the jitter spaces of that cutoff order, which is pretty high. So when you use that cutoff, when you use a cutoff you derived in this way to say, for example, cutoff in Feynman diagram, for example, that would be a local excitation. So the meaning of cutoff seems to be a little bit extrapolated from the original derivation.
I agree. Using this as a cutoff on one particle Feynman, a few particle Feynman diagrams, particularly for very large boxes, like if I take this to literally be the size of the cosmological horizon, that gives you a cutoff at the energy density associated with the cosmological horizon, which is completely crazy. That's
yeah. So I think that to be it seems like you said when you say cutoff in energy, it can be various different things, and it seems like here you are using cutoff derived in one way to a rather different situation.
Well, I hasten to add that it's not me, because this was the interpretation.
Yeah, you are reviewing that, but yes, still, yeah.
So I'm saying let's not use this at all as a UV cutoff, but instead use it as the sort of scale at which there may be some change in quantum field theory, but it can turn out to be an extremely mild change. So, so what I haven't told you yet is what you get for G-2, or how corrections to G-2 might look if you use this depletion idea instead of hard cutoffs. I'll get to that in a second, and it's extremely mild. So what, indeed, what does this cutoff mean? What's the change in quantum field theory? Putting a hard cutoff is an extremely violent act, particularly if we were talking about quantum field theory in very large boxes, and we would like to do something a little bit less crazy. Okay. Okay, yes, and that indeed is what I'm about to talk about. So we can do enormous violence to the Hilbert space, I claim, and the results for few particle matrix elements, product states and things, will still look like ordinary quantum field theory. So one way to see this is to take a model, and don't take this as a serious thing, just a toy model. So let's try and model the depletion as a real finite volume effect. And we know that quantum field theory is very volume insensitive, even if we have light particles. So most processes, we can put them into a box, and finite volume effects are very small. And the types of boxes that we're talking about here, this effective CKN volume that's setting the depletion rate in our interpretation, they're absolutely enormous. So if we talk about energy scales of order the electron mass, which is what's relevant for G-2, the CKN box size is 10 to the 5 kilometers. Okay, so this is an enormous box. Nobody cares. You know, when you do G-2, how sensitive is G-2 to finite volume effects? You could put it in a box of size 10 nanometers, and that would still not make a detectable correction to the observable at current precision. So in terms of energy spacings, this is saying, all right, let's just use, instead of completely continuum quantum field theory, let's use QFT in a box with sort of 10 to the minus 15 electron volt momentum spacing. The current experimental sensitivity is 10 electron volt momentum spacing. All right, so we can throw out a lot of states and still get ordinary processes bang on. You can do the same thing for the muon or other energy scales. Just to give you one other energy scale, if we're talking about a 10 TeV sort of scale process, the IR cutoff from the CKN bound, or as we're interpreting it, a momentum resolution, is something like 0.1 electron volts. All right, the LHC and future colliders are not going to be sensitive to that kind of momentum resolution. All right, so to summarize, the hard cutoffs give you these effects that, for example, for G-2 go like 1 over root M Planck. And the state depletion thing, I haven't shown you the calculation, but you can compute it and see that it goes like 1 over M Planck squared. It's an ordinary G Newton type effect. CKN originally said, well, maybe this is relevant for the CC problem. As someone already pointed out, the UV cutoff in a box of horizon size is at the energy density associated with the vacuum energy. So that sort of trivially cuts off the integral, but that's too strong. We need something a little bit more nuanced. So we can take the depleted density of states and stick it into the very naive computation of the one loop vacuum energy. And so if we don't do, if we use the ordinary density of states, of course, there's the usual quartic divergence. But this is a counting that allows for modes of momentum spacing 10 to the minus 33 electron volts at all scales. Certainly, we have not tested that in any experiment. And if instead we use this depletion, then you get something which is comparable to the observed value. Here I'm reporting the total energy in a horizon volume. So the strong suppression above the observed scale means you have many fewer modes contributing their half h bar omega, and you get something which is compatible with the observed value.
Sorry, Patrick, are you saying that if I take into account these effects in the sitter for any quantum field, the vacuum energy that I get for that quantum field is of order the observed vacuum energy density?
Yeah.
That's cool.
So that was sort of at the level of just a flat space computation. We have to bring it in a little bit so we can ignore curvature effects, but yes, that's the claim.
Patrick, sorry, can I ask you a quick question?
Sure. Yeah,
about
please.
this? I mean, what about things like the QCD, non-perturbative contribution to the vacuum energy? I mean, the thing, and also for that matter, the shift from the Higgs. So things which are sort of not, well, possibly in the QCD case, of course, loop level, but those things.
Right. Yeah, I would say that anything that's clearly a classical contribution, I can't say anything about. That's still there, and we still have to worry about that. So all I'm talking about is sort of the far ultraviolet radiative correction. I think anything that, like the QCD contribution, that's measured, that's there. Well, okay, I need to think about the chiral condensate, but I would.
Yeah,
I would
the chiral
just
condensate
that like the Higgs.
indeed, it's a somewhat different thing. Exactly. I mean, so
Yeah.
okay.
Yeah, I don't think I can say anything about that. Yeah.
Right. Thank you.
Okay, just a brief comment on some more sophisticated versions of this stuff, mostly due to Tom and Willie. So a more covariant version, you might object to the kind of very non-covariant presentation so far. A more covariant version is to take the covariant entropy bound, which applies to causal diamonds, promote it to the covariant entropy principle, which says that the log of the dimension of the Hilbert space needed to describe physics of a geodesic observer associated with a causal diamond is the area of this so-called holoscreen, this thing in blue here. And the CKN covariant entropy principle is just that the number of kind of local QFT-like degrees of freedom goes like A to the 3/4, where A is the area of this holoscreen. You can generalize the thermal argument and the number of dimensions. So like this. The question about the de Sitter and cosmological horizons, instead of just requiring that L is bigger than the black hole radius, we now need to require that the cosmological horizon is also bigger than L. This is how we deal with boxes that are larger than the Nari radius in de Sitter. But in all of these generalizations, we would still like to imagine that whatever the theory of quantum gravity is that applies, the depletion of states relative to ordinary bulk QFT had better be pretty gentle. A few just kind of related properties of de Sitter space, and I'm almost done here. One more slide. So now that we've mentioned causal diamonds, it's worth noting this is all connected to de Sitter space because the maximum causal diamond in de Sitter is the static patch, and a lot of people have worked on formulating holographic theories of the static patch. So the covariant entropy principle suggests maybe we need a finite Hilbert space to describe quantum gravity in the static patch. And a very interesting possible insight to what this theory might look like is the semi-classical fact that if you put a black hole in de Sitter, it lowers the total entropy rather than increasing it. It pulls in the cosmological horizon more than it contributes in black hole horizon. And this suggests that perhaps localized excitations are a constrained state rather than sort of a thermal state. So this is also reflected by Euclidean path integral methods. You can take Euclidean Schwarzschild de Sitter. It's not a real solution. You have to impose a constraint that essentially fixes the mass of the black hole in order for it to be a real solution. And it shows the same entropy deficit. And it's a huge entropy deficit that actually scales like the square root of the total entropy for small masses. This is a similar scaling, as been noted many times and most recently in some work by Susskind. This is a similar scaling to matrix models. If you take a large matrix degrees of freedom and then you start setting some of these column vectors to be constrained to 0, and you count how many degrees of freedom are left, it has the same kind of root S scaling. So perhaps that's a hint to the nature of that theory.
Patrick, I thought this also holds for large black holes in de Sitter.
Yes, yes, the deficit holds, but the precise scaling here, this is no longer correct. Minus M over TC is no longer correct.
Yes, yes.
Yeah. Okay, so I'll just conclude with some free association here, plausibly related ideas. The computer scientists have made much of the fact that you can efficiently map high dimensional spaces to low dimensional spaces while preserving inner products. And this has been recently discussed in ADS-CFT in the context of these non-isometric bulk boundary maps. I'm told that you guys had a talk recently about this. So this nice work by Akers and Pennington. So that's, I think that's clearly related to this. We would like to know how we get the physics of ordinary continuum bulk QFT very efficiently out of some much smaller Hilbert space. And in lower dimensions, there's been a lot of work and recent success in actually working out some of the microstate physics and matching the DS3 horizon entropy, in particular to CFTs with a TT bar-like deformation. This is work from Stanford and others. There's been a lot of work on matrix models and DSLography, also in lower dimensions, and some work on connecting this to Ryu Takanagi type formulas by Susskind and Shibulian. And finally, I just want to mention this paper by Tom, where he sort of goes into possible connections and also collisions with some of these ideas with the swampland conjectures, and I recommend that to everybody. It's not quite an easy read, but stimulating. All right, sorry for going over time. I'll stop there and hand it off.
Okay, so let me try to share my screen. Okay, so can you see the screen?
Yeah.
Yeah, everything's fine. Okay. So since the idea is to try to make this into a discussion so that everyone can basically participate and we can have a nice exchange, I will just try to very, very briefly comment on 2-3 main points that I think may be useful to trigger this discussion, and then hand over to everyone around. So the idea is, first of all, the first point I want to convey is the fact that, oh, this is not, okay, is the fact that entropy arguments for swampland conjectures have been already used. I mean, they've always been there, and in some cases they've been like heuristic arguments, in some cases there's been like motivations and so on. So we all, like, probably the first times that we heard about no global symmetries or the weak gravity conjectures, we heard about this kind of arguments. More recently, there's been, for example, the argument for the refined de Sitter conjecture, which is basically combining the swampland distance conjecture with the covariant entropy bound and saying that then close to the boundary of moduli spaces, the scalar potential for a field goes as the species number somehow to some power, so that basically one recovers the behavior predicted by the distance conjecture, by the de Sitter conjecture. Another very recent application, for example, are these entropic arguments in favor of, in this case, the magnetic with gravity conjecture somehow, which is quite nice because in this case it talks about, I mean, this basically requires towers. It's kind of different from the original argument for the weak gravity conjecture in the sense that instead of talking about the requiring the instability of these black holes so that they can decay and then preclude the contradiction with entropy bounds, this is somehow different. That's the reason why it talks about the tower versions, and it can also be related to the swampland distance conjecture. But basically my message here is the fact that this is probably an interesting avenue. Like, in order to connect entropy bounds to IR physics or to whatever kind of measurable physics that we want to do, it might be a useful thing to try to understand swampland conjectures in this context. So this being said, and the other, let's say, concept that I think can play an important role here, and it's interesting to mention so that we are all on the same page before going into the discussion, is the species scale, on the other hand. And the species scale may appear from the effective field theory point of view as a very mystic scale or something like that, because basically what it says is that in the presence of n light degrees of freedom coupled to gravity, basically the scale at which gravity becomes strongly coupled is not the Planck mass, but actually the Planck mass over the square root of the number of light states. So basically the cutoff for the effective field theory is corrected from the naive expectation by this factor of 1 over the square root of the number of light species. But an interesting thing here, again, in connection with the swampland, is the fact that it fits very naturally with the idea that once we have light towers of particles, the cutoff for the effective field theories must go to 0. So it can be nicely connected to the swampland distance conjecture and so on. But also it's quite interesting, and it might be useful in this sense to think about it, about its interpretation somehow in terms of the fundamental scale behind it, because it's somehow like a bit confusing, because from the effective field theory point of view, there are some arguments you can kind of justify, like argue for this scale in terms of the renormalization of Newton's constant, some black hole arguments, some thermodynamic arguments. But it's very illustrative, I think, to, for example, consider an effective field theory of a lower dimensional effective field theory. One has some Planck scale in this lower dimensional effective field theory. And once one goes to the compactification limit, the KK modes become light. They would enter as light species here, and basically they would change the real cutoff of the theory. And it is plain from that computation, and one can see that actually this species scale from the lower effective field theory point of view turns out to be just the higher dimensional Planck mass. And something similar can be done if one considers a tower of excitation modes of a string, and actually the fundamental scale of quantum gravity turns out to be the string scale up to logarithmic corrections. But the idea is that this is somehow giving you, like in terms of the effective field theory, it's giving information about the fundamental scale of gravity in effective field theories. So finally, and before going into the open questions, I just wanted to introduce these two things. And then finally, I want to connect with what Patrick was saying, the CKN bound or entropy bounds in general, but now also including this species scale. And basically, I just want to very briefly comment on the result that actually by playing this kind of games, one can somehow find evidence for the ADS distance conjecture from the species scale and the covariant entropy bound. So one can try to play this very simple game that Patrick mentioned before. Now, instead of for gravitational collapse, one just takes the scaling of the entropy with the volume that naively one expects from a quantum field theory. This must be bounded by the covariant entropy bound, in particular, for if we apply to a surface, to a closed surface of length, typical length L. And this gives this kind of UV-IR mixing if we identify the IR cutoff as the size of this box. Or actually, let's say, since we are talking about entropies, this is just the size of the closed surface to which we can apply the covariant entropy. Now, the thing is, if one combines this, or if one identifies this UV cutoff with the species scale, we were saying before, so for a tower of states, the typical thing that happens in string compactifications when one goes to boundaries of modular space, or when one goes to weak coupling points and so on. So if one identifies this UV cutoff with this species scale for some tower with some effective parameters, just some characteristic max scale and some P that gives basically the spacing between the steps in the tower. And then what one can do is to apply this to ADS, in particular to a surface in ADS of length, the ADS radius. What one gets is precisely this inequality, which is morally the ADS distance conjecture, in the sense that when we make the cosmological, if we have, for example, now a family of vacua and we make the ADS, the cosmological constant go to zero, basically one gets that the scale, the mass scale of the tower has to go to zero as well, where this alpha is just a number, positive number that only depends on the dimension and on the characteristics of the tower. But the point here is that morally, and playing this game very naively, one can get this kind of results, and it's kind of shocking because this seems like a very easy thing to do. But there are all these open questions that Patrick was mentioning before, and that are also in the questions from the audience about what's the real interpretation of these scales and so on. So basically, what I want to do is to just now go to these open questions, and I will throw some questions for everyone in the audience, and then we can finally start this discussion, even though we already have some of this. So basically, the first one already was there, like before, and it's really what's the meaning of this scale, this lambda UV or this lambda IR, or what is really the way in which the effective field theory is breaking? So is it like, can we really encode the breaking of the EFT in just some cutoff, or there's some prescription in which we have to take out some states that would naively be there for the quantum field theory without gravity, but are not there in the presence of gravity? For example, this kind of depletion of states that Patrick was talking about. So what's really, is there any universal, let's say, model independent way in which, let's say, the defective field theory is broken somehow? In particular, in this context, what's the role of gravitational collapse is important, because this is basically applying this instead of to the covariant entropy bound to this CKN bound that we were just saying. And in general, in this general context, I think it's very important to try to address the question of how much of the information contained in some of these swampland conjectures can actually be recovered or motivated in terms of entropy arguments. It's in the sense that these are statements about the full theory of quantum gravity, but then how much can be basically encoded into statements about the entropy or things like that for the effective field theory, for example. Is it all of them? Is it much of them? Is it just part of that? So with that, then I also want to include the questions that Patrick basically had about his first part of the talk. I don't know if now, Patrick, maybe you want to comment something about that. And if not, maybe you can just open the finally the thing for discussion.
Yeah, since yeah, just in 2 seconds. So sort of asking whether or not the things that people have done with matrix models or DSTT bar or DSDS and so forth, or these sorts of random projections that have been talked about, whether this strikes a bell with anybody and seems to have any connection to the swampland program. But yeah, as Alvaro said, let's just go ahead and open it up now, since